So, hello, I'm John. I'm going to be talking about coroutines and gRPC. Is the clicker working? Yes, the clicker's working. So, first of all, why am I interested in gRPC and coroutines? Well, I work at Oxford Nanopore, and we make nanopore sequences for DNA and RNA and other biomolecules. And we've got two main bits of software that we're going to worry about today. We've got the core, which is written in C++, and we've got the UI, which is written in TypeScript. And in between them, there's a gRPC communications channel. And that's actually quite nice. It means that the scientists can check on the progress of their experiment from the office rather than having to go back to the lab every time. So in the core software, we implemented gRPC server, and we want to implement it in a performant way, but also in a straightforward way. And as we'll see, it's easy to implement gRPC server in a straightforward way, less so in a performant way. So the outline of the talk, first of all, we're going to have an introduction to coroutines and gRPC, and then coroutines and gRPC. And that's kind of like background and where we want to end up. Then we're going to look at writing the coroutine support code that allows you to actually write the coroutine we want to write in C++. And we're going to build that up in 3 steps. We're going to first of all do the most simple coroutine, then a really simple gRPC coroutine, and then a more complicated gRPC coroutine. And we're going to finish up. We've got a summary, we've got further steps, we've got resources for you to look at, and some of the directions that we could go after this talk. So, who here has written a function that calls another function? Hands up. Great. You know what I'm going to say. You've got a function that you're writing, and you start executing your function at the entry point. The function executes until you call your subfunction, at which point the parent function is suspended and its state is saved. So the parent function stops executing to go and execute the subfunction. Then we execute the subfunction. That's happy, that's done. We come back to the parent function, at which point the parent function's state is restored and the parent function resumes executing. And it keeps executing until it hits the exit point. Straightforward function call, everyone knows this. Local variables are preserved across sub-function calls. Everyone's happy with this. If you've got I before you call the function, you also have I after you call the function. Let's have a look at coroutines. Now, the first thing you'll notice is that this looks very similar to the previous slide. Again, you start executing your coroutine body at the entry point, and you continue, only this time we've got a suspend point instead of a sub-function call, and this is a special coroutine thing. And at the suspend point, the coroutine is suspended, the coroutine state is saved, just like in a normal function call. And then something happens, control goes somewhere. The coroutine doesn't care where control goes, it just knows that control is no longer in the coroutine. And at some point later, someone can resume the coroutine, at which point the coroutine's state is restored, the coroutine is resumed, and everything continues like a normal function call. And then eventually you get to an exit point. And just like with functions, local variables are preserved across the suspend points. So if you have a variable up here, the variable is also available down here, and it's also available for the entire duration of this, which turns out to be really handy. And as you've probably noticed, from the coroutine's perspective, a suspend point looks just like a subfunction call. But now let's look at the perspective outside the coroutine. So this is someone that's calling the coroutine or resuming the coroutine. So the caller calls the coroutine starts executing the entry point, gets to the suspend point, the coroutine state is suspended, the coroutine saved. So this is exactly what we saw before. And then at the suspend point, control returns to the caller and the caller continues executing. And the coroutine is just sat there not doing anything. And at some point later, a resumer can come along and resume the coroutine. The coroutine's state is restored. The coroutine is resumed. It picks up from where it left off, continues executing. And then when the coroutine finishes executing, control returns to the resumer, and the resumer continues executing. And so you can see from the caller or the resumer's perspective, this looks like a normal function call. You either call or resume your coroutine. Control goes into the coroutine, control comes back out of the coroutine. The caller and the resumer can be different functions, so you could hand off your coroutine to another thread, and it could be resumed on another thread. And you can also return an initial return value from the coroutine when it reaches the first suspend point. And you can have a coroutine yield a value either when it finishes or when it reaches the suspend point. And yeah, that's coroutines. Any questions? Hopefully not. Good. Let's press on. So, yeah. Yep. Yes, it can yield any suspend point, and the end is a kind of just a special suspend point. So yes, I've only shown one suspend point. A coroutine can have multiple suspend points throughout its lifetime. I've just shown one for simplicity. Yep. Usually you construct things such that you can only resume a coroutine once it's already been suspended. So in normal usage, that can't happen. You don't get the token to resume the coroutine until the coroutine has been suspended. So from the coroutine's perspective, this is what we just covered. Suspend point looks like a normal function call, but it's not limited to just calling a function. From the caller or resumer's perspective, calling or resuming a coroutine looks like calling a normal function, and control returns to the caller or resumer when the coroutine suspends or ends, so just like a normal function call. Coroutines need to be resumed by something somewhere, so it's not magic. They have to be resumed on a thread in order to continue running. And so you need to plan up front when you're going to resume your coroutine. And finally, a function is a special type of coroutine. It's just one that doesn't have any suspend points, which I think everyone could agree with. Cool, so that's coroutines in general. This is now coroutines in C++. So a coroutine is any function that contains one or more of these three keywords. In a kind of tautological sense, any of these keywords in a function body turns into a coroutine. And what do we mean when we say it's turned into a coroutine? What we mean is, in the C++ case, the compiler generates some coroutine support code. From the outside, so if you look at the function signature of a coroutine, you can't tell the difference between a coroutine and a normal function. It's got a return type, like just as ever. You don't have to put special keywords around when you call the coroutine first. And calling a coroutine returns the initial return type that's specified in its signature. And this initial return type defines the behavior of the coroutine, but it's not related necessarily to what co-yield or co-return produce. We said it depends on the initial return type. And what we mean by that is you can use coroutines for lots of different purposes. We'll look at two of them coming up. And in C++, that initial return type defines how a coroutine operates, what kind of coroutine it is. So there's two sides to coroutines. There's the language support and there's the library support. The language support is pretty good. The library support is pretty poor. There's a std generator coming in C++23. It's in GCC 14 now on the latest Clang trunk. There's also some third-party coroutine support libraries. So if anyone's used Boost ASIO, that's got pretty decent coroutine support with support for a lot of compilers. And in the following examples, we'll assume that there's some library code available because we're focusing on the uses of coroutines for the next few slides, rather than how to write a coroutine and what code you need to support it with. So we're going to look at a generator. And a generator is an object that yields a sequence of values. And sequence implies that we remember where we've got up to, and we know where to pick up when we produce the next value. Coroutines remember state. Sounds like a job for coroutines. So coroutines have local variables. They've also got a memory of where it's got up to. You can imagine the program counter is also part of the coroutine state. And they know where to resume from. So this is using std generator. All it does is it loops forever and yields integers starting at 0, going up and up and up. So every time you resume the coroutine, it yields the next value. Like we said before, the behavior depends on the initial return type. So this is a When you call IOTA, you get a generator object back, and that kind of manages the coroutine body. Remembers I between calls, just like we said. And when we co-yield an int, and that ties into this int here in the generator. And the coroutine continues from the co-yield point when it's resumed. So it runs through, yields I and stops, and then when it's resumed, it picks up from where it left off. And you can use it with ranges. So this code with std print and all that kind of C++20 niceness, C++23 niceness, prints exactly what you'd expect. Any questions about generators?
So there's no return statement, so this looks very much like a generator in Python.
Yes, this will run forever. You can also return at the end as well. Return the final value. Yeah, so when we call IOTA down here, we get a temporary generator object, and then that does a standard ranges thing. I'm not going to talk about generators anymore in this talk, but I don't think you can really do a coroutines talk without talking about generators. It's one of the primary uses for them, and as you say, people from Python are really familiar with that usage of them. So we're going to look at tasks, and tasks allow you to write asynchronous code that reads like blocking code. So you get the performance of asynchronous implementations without having to have all the callbacks everywhere. And we're going to write a simple blocking file copy function. So this is my toy function. You've got a blocking read, a blocking write, and copy file overall is blocking. So when you call copy file, the caller can't do anything else until the file has completed copying. So we said you can write asynchronous code that reads like blocking code. So let's turn this into a task-based coroutine. And it looks very, very similar. So what we've added an initial return type of a task. So when you call copy file, instead of copying the file, you get back a task object. We've also replaced read and write, the blocking functions, with these coroutine aware async functions that we can await on. And this is what it looks like from the coroutine's perspective when you run through this function. So you've got this standard async read call that starts the async operation and returns something that you can pass to operator co-await. And then when co-await is encountered, the coroutine is suspended until the async operation completes. At which point, someone somewhere, and we'll get into this later, resumes the coroutine. It picks up from where it left off, and it gets the data that it read from the file. And then you do an async write. Again, that's a normal function call. It returns immediately. It kicks off the operation. And then again, you co-await on the returned awaitable, and the coroutine is suspended. Then finally, once the write completes, it comes back, and then control flows off into the coroutine. Happy? Good. So we said that calling copy file doesn't actually copy the file. It just returns this task object. So that's it, returning this copy task when you call copy file. And a task object represents work that needs to be done. Calling the coroutine just returns a task object, doesn't actually do any work. And the coroutine is suspended before executing the coroutine body. So when you call copy file, you get an object back that represents this object when you execute it is going to copy a file, but it doesn't do anything to start with. And that turns out to be really useful to avoid race conditions or destruction, exception safety, because no code in the coroutine body is executed before we're ready for it to be executed. So you do all of your setup and then start running your asynchronous code. To actually do the work, we need to execute the task, and typically you'd submit it to something called an executor, which sounds very fancy. The executor resumes the coroutine and does some work. And then when your async function completes, the task is again posted to the executor resumes it, and it picks up from where it left off and does the next bit of work. And at its simplest, an executor is just a list of tasks and a thread to run. And so the thread pulls a task from the list, resumes the task, pulls the next task from the list, resumes the task. So this is what it looks like from the executor's perspective. So the executor is running, it's reached our task, it pulls the task from the list and it resumes it, and it starts executing the coroutine body. And remember, we said the coroutine was suspended just before executing the coroutine body when we made the copy task. Now we're resuming it and starting from the beginning of the coroutine body. It calls async read, which starts the async operation, and then we hit the co-await. And what happens there is the coroutine suspended, like we talked about before, and also it registers so that the task is scheduled to be resumed on the executor when the async operation completes. So you can imagine that a normal async function might have a callback, and you might say in the callback, stick this task on the executor in the callback. Control returns the executor, and now the executor is free to execute other tasks. So this is the async concurrency side of things. At some point, your async operation completes, the task is posted, the task is picked up by the executor and resumed, returns the data for coroutine, you hit your async write function, which again starts the async operation, hit the co-await, which does the same thing as before, and control returns the executor, and again the executor can resume other tasks. And then finally, when the async write operation completes, it picks up the coroutine, resumes it, there's nothing to be done, the coroutine finishes, it's not scheduled to be resumed again. Happy with that? Blocking operations inside the coroutine will block the executor thread from running other tasks. So if you want high parallelism, you don't want to block this executor thread. And there might be a thread pool, but even so, if you want maximum throughput, you don't want to block it. And that's a fairly standard pattern when using async. Yep.
The problem that I see is that async read and async writes don't exist. So you have to create them yourselves based on blocking functions.
Yeah. Based on blocking functions, do you say?
Yeah. The operating system will. Yeah.
So they're implemented in Boost ASIO with callbacks, and actually Boost ASIO just works with coroutines. So you can start an async read in Boost ASIO, and it will give you back an awaitable. There's also other async implementations that take callbacks. So you kick it off, and it takes a callback, and the callback is called when the task completes. That's a fairly standard pattern. So these aren't blocking the async read and async write. They just call the callback when they're done. And yes, they happen somewhere in the kernel. There's another thread that runs the callbacks, all this kind of thing. But we don't worry about that from this perspective.
The two things that I noticed that might impact performance for particular use case I might have, which are memory allocation, sticking these things inside the executor.
Yeah.
And also the fact that there might be multiple threads and thread boundaries to cross. Are there options whereby you can change your allocators or execute on the thread that you run?
Yep. So that's part of when you do your design, you pick a certain executor type. And yes, inside coders, we want to talk about it today. There are options to use custom allocators. There was a Gornishinov talk, and he used coroutines to hide memory access latency. And so he basically kicked off a load of memory accesses in sequence. He was like doing lots of lookups, kicked off a load of memory accesses in sequence, and by the time the final one had kicked off the access, the result was ready in the first one. And he was it was fast enough to hide memory access latency. So they're pretty performant if you work a little bit at it. Right, that's coroutines. We're going to talk about gRPC. Hands up if you used gRPC or some other RPC library. Cool, you already know what I'm going to talk about. You've got a server and a client. The client sends messages to the server does some work, the server returns a response to the client. And if you've got a decent implementation, it will provide some abstractions for you to use. So on the client side, you might have helper functions to connect to a server, to call an RPC to receive a response. And on the server side, you'll have helper functions to listen to requests and call application code when the client calls your RPC. Yep. gRPC is an RPC implementation that was started by Google, although they claim that the G in gRPC doesn't stand for Google. I think they're lying. These are defined services, calls and messages in protobuf, which is this kind of interface description language. And then there's a compiler that takes the description and spits out C++ code, or spits out Java code or Python code. There's 4 different call types. There's all of these, and basically how many messages does the client send, how many messages does the server send. And there's these implementations. So there's the synchronous implementation, where you basically have one thread per simultaneous call. There's the async, which uses an event loop, and you've got to run the event loop yourself. It's quite tricky to use. And there's reactor or callback implementation, which is built on top of the async implementation, but takes a lot of the pain out of using it. So basically, you get a callback when an operation completes. And that sounds like just the kind of thing we want to be able to hook into for our coroutines to work. So we're going to focus on unary and server streaming calls. And we're going to look at the synchronous implementation and the reactor implementation. And we're going to look at the C++ code we have to write without using coroutines to support some basic use case. So we're going to write a simple server streaming RPC call, which the client says, send me 5 responses, and the server sends 5 responses and then says, everything went well. We're going to use the synchronous implementation, and we're going to use the reactor implementation. We're going to compare and contrast the code we had to write for both of them. So the synchronous implementation is pretty straightforward. You've got request and response up here, and their message types are defined in our protobuf file. They've been compiled into C++ types, and you can read the count from the request. You can set an index in the response. gRPC gives us this server writer object, and we can use that. We can call write and give it our response, and it'll write that response from the server to the client. And this is the blocking function, and remember, we're running on one thread per simultaneous call. So this blocks the thread until the write's complete. One nice part of this is that if you want to, say, sleep for 30 seconds and then return a response, you can just use a blocking sleep because you're burning a thread anyway. One other thing to note about this is it's a really obvious loop. You can see exactly how many responses we're going to send. You can see that it's going to loop and write, and then it's going to finish. Yep. Let's look at the reactor call now. So we said the reactor call is based around callbacks. And so what we do is we make this new reactor, and we return it to the gRPC there. And then the gRPC there calls callbacks on us, and we can call functions on the reactor base class, this server write reactor, to kick off asynchronous operations, and then the callback gets called when the asynchronous operation completes. Reactor is a multiplex and internal gRPC thread pool. So that's similar to the execution that we saw before. There's an execution that runs on a thread pool inside gRPC. It's scalable, and again, like we said, you don't want to have blocking functions inside your reactor, because that'll block the gRPC thread pool and hurt your throughput. We need to write that class, so let's look at how we write that class. So the server write reactor that we're going to use, you have to call start write to kick off the first write, and at that point, you want to return to the gRPC there, and then when your write completes, the gRPC there will call this on write done function. Then you keep doing that until you've sent all the responses, and then you call finish with a status. And then when the gRPC there is completely finished with you, you get this on done callback, at which point you have to clean yourself up. It's a really weird idiom and it looks really funny in the code, but it's just what everyone has to do. So inside the reactor class that we're going to write, we need to call start write when the reactor is created to kick off the first write to kind of prime the pump. And then we're going to override this on write done callback that's in the base class. And we're either going to call start write to kick off the next write, or we're going to call finish when we've done all of our writes. And we need to override on done to clean up the reactor afterwards. So this is what it looks like. It's not that complicated, but it looks like quite a lot of code. Some things to note are we need to keep track of state across the asynchronous calls. Hey, coroutines can keep track of state across asynchronous calls. We need to keep this response object alive from when we send it here to when the write completes over here. So again, we need to keep an object alive across effectively an asynchronous call boundary. Again, coroutines do that automatically. And there's a loop in here, and it's a lot more difficult to spot than it was in the previous synchronous case. And the loop if you haven't spotted it yet, is here. We call start write. And then when the write completes, on write done is called. And then in on write done, we call send, which then calls start write again. And our loop variables, we've got one loop variable being incremented over here, and it's being checked against the target over here. So it's quite difficult to follow the logic of the code because it's split across two functions, and there's this asynchronous call and some magic in between to call on write done. So when we write a reactor, we need to manually manage state. There's quite a lot of boilerplate code to write. But I think the key thing I don't like about reactors is that it's difficult to combine functionality. So if you wanted to send a response every minute, you need to write a different reactor. If you wanted to send responses as data becomes available, you need to write a different reactor. If you want to send a response every minute or when data becomes available, you need to write yet another reactor. It's difficult to just combine these other two reactors. So how can we use coroutines to make our gRPC code nicer? So to recap, the synchronous code was easy to follow, easy to combine functionality because you can use blocking calls, and performance suffered. The reactor code was performant, but it was more difficult to write and maintain, and it was difficult to combine with other functionality. So we want to take the good bits out of both. So we start by writing the code we wish we could write. I can't remember who said it, I heard it in a talk. A good way to design something is to write the user code that you want to be able to write, and then try and write the support code to enable that user code. So we remember from the first part that task-based coroutines can make async calls look like blocking calls, but underneath the hood, they're async and performant. And ideally, the whole of the stream responses call body could just be a coroutine, so we can use co-await and co-return directly inside the function body. So this is the code that I think we would like to be able to write. We've got our really obvious loop back. This co-await send is an asynchronous call that looks like a blocking call. We've got a co-return at the end. And this, to remind you, was the blocking code. And you can see, just as before with the file copy example, the blocking code and the coroutine code look very similar, just with a couple of extra keywords in there. So it turns out, if we write some support code, we can actually write exactly this and have it work today. This co-await send response, what we're going to do is we're going to suspend the coroutine, we're going to start sending the response, and then when the response is complete, we're going to resume the coroutine. That's fairly standard. And similarly, when we hit the co-return statement, we're going to finish the call with the supplied status. So this is a kind of diagram of what I've just said. You start executing the coroutine, you get through to the start write call, the coroutine's suspended, you call start write, and control returns to gRPC thread pool. And then when the write's complete, this on write done callback is called in your reactor, and in that callback we want to resume our coroutine, keep executing, and then eventually finish gets called and control returns to the thread pool again. So the benefits, it's simple to write the code, it looks just like the synchronous code, modulo a couple of keywords, but you get the performance of using the reactor implementation. And another nice thing about what I've just shown you is that it's impossible to get the call order wrong. So in gRPC, you can't have two writes in flight at once. Well, because the coroutine's suspended when you reach co-await and isn't resumed until the write is finished, you can't have two writes in flight at once. Similarly, in gRPC, you can't call anything after you call finish. The only thing that you can do is tide yourself up in the on-write done callback. And with co-return, you can't make any other calls after you finish. And you don't need to worry about exceptions in the same way, because with C++ coroutines, you can specify a custom exception handler if an exception escapes the coroutine body. The other nice bit about it is it's composable with other coroutine calls. So if you have a coroutine-aware async timer library, you can co-await on your timer, and then you can do some more gRPC stuff afterwards, and you don't block the gRPC thread pool. You can have async waits for data to become available. You can even have async network or file system calls. And obviously, your gRPC writes are an async network call, and we saw the async file system calls earlier. So in summary, C++20 has language support for coroutines, but not much library support. Task-style coroutines can make async code look like blocking code. gRPC does have this nice performant reactor implementation, but we saw the code is not very nice. And we imagined the code we'd like to be able to write. It reads like blocking code, performs like reactor code, it's safe to use, and it's composable. Awesome, let's get on to actually writing some coroutine support code. Any questions from the first part? No? Perfect. So like I said at the very start, in this section, we're going to write support for the simplest possible coroutine that we can imagine. Then we're going to write support for this co-return status that we wanted to be able to write. And then we're going to write support for this co-await send response. And obviously this one is a bit more complicated because we need to resume, whereas in this one we don't need to worry about resuming because we're finishing. So what's the simplest possible coroutine? I think it's this. It does absolutely nothing, but it's got this co-return keyword in there, which means it's a coroutine. So all of the compiler's coroutine machinery kicks in. This coroutine returns this initial return object to the initial caller. And we said before that the initial return type determines the behavior of the coroutine. Co-return doesn't return anything. So then there's an obvious question of, if we're returning an object, an initial return object to our caller, where does it come from? It can't come from co-return because we're not co-returning anything at all. And the answer is the compiler calls a user-supplied function to make the initial return object. And we'll see that function in just a second. And this function is part of the promise type. And we're going to dig into the promise type. And the promise type defines the behavior of the coroutine. So it says what happens when the coroutine is first called. What happens when you hit a co-return statement. So the compiler looks up the promise type by looking up std coroutine traits with your initial return type and the args. And by default, it looks up the promise type inside this initial return type. And so that's why I said before that the initial return type defines the coroutine behavior, because it looks up the promise type based on the initial return type. And so I'm going to do some live coding, and I went to a coroutines workshop with Matthias Putz, and his idea was let the compiler guide you. So we're going to have a go at that right now. We're going to implement this, get it compiling and working. So this is the code. And as you can see down here, we've got an error. And it says this function cannot be a coroutine. This coroutine trait's initial return type has no member named promise type. And we remember that by default, coroutine traits looks inside the initial return type to find the promise type. So let's go ahead and add a promise type inside our initial return type. So the compiler error message in the bottom right has changed. It's now saying there's no member named initial suspend and there's no member named return void. Okay, well let's add initial suspend. So I happen to know that the coroutines library contains this suspend never, and if you return it from initial suspend, it won't get suspended. The coroutine won't be suspended when it's first called, and that's why I said about the coroutine being suspended or not before the coroutine body starts executing. Right, no member named final suspend. So if suspend never was good enough for the initial suspend, let's use it again for final suspend. Okay. The expression co-await promise final suspend is required to be non-throwing, and it suggests we add no except. Okay, let's add no except. No member named return void. Let's just do nothing when we hit the co-return statement. You'll notice there's a lot of doing nothing in this coroutine. No member named get return object. So this get return object function is how the compiler knows how to construct this initial return object that it needs to return when you first call a coroutine. And initial return is empty. So again, we'll do nothing, we'll return an empty object. Happy. is required to declare the member unhandled exception. And does that compile? Yes, that compiles. And you'll see we've implemented these 5 member functions. The compiler is now happy. But you'll see on the right-hand side, that's an awful lot of code. I thought C++ was meant to be efficient. I thought coroutines were meant to be efficient. Oh, it's capital O, isn't it? But if we put O1 in there, it compiles down to nothing. And that makes sense, right? Because we start the coroutine, we don't suspend, we execute the coroutine body that just returns, and in the return void, we don't do anything special. And then we get to the final suspend, we do nothing. And so we've generated some really nice code from our coroutine. And importantly as well, we don't need an allocation. We don't need to allocate anything because we can do it on the stack, because the compiler can see that our coroutine just runs straight through, doesn't suspend, and therefore it's just a normal function. And like I said before, a coroutine with no suspend points is a normal function. So I'm just going to, for fun, I'm going to add an atomic int, and obviously the compiler needs to generate writes to this atomic int anywhere they happen. So in get return object, we'll say I equals 1. In initial suspend, we'll say I equals 2. Return void. Actually, in the coroutine body, we'll say I equals 3. Return void. And final suspend. And you can see, oops, it's not happy. I don't know if it's because my internet connection is unhappy. Oh, there we go. So you can see on the right, we write 1 to I, we write 2 to I, 3, 4, 5 to I. And so you can see the order these functions are called in matches the numbers. Happy? Cool, let's go back. It worked, aside from the internet connection thing. So this is the answers, just in case it didn't work. You'll notice we've got a lot of const explorers in here, and they do nothing, so of course they can be constant. Yes?
If I have lots of functions like this, how much is the compile time worse than just having normal functions?
I've not looked into it. I think probably, for me, the ease of code writing would outweigh the increase in compile time.
As a practical example, someone replaced one of the systems I Googled with coroutines, and the finding was that because you can hide the memory allocation, as you were saying, the effective goal was that the new system written with that coroutine support library was 10% faster without any other change.
The other nice thing that came from the Gornishinov talk that I said before was that he found that the code that he wrote with coroutines was more efficient than his handwritten code, because the compiler could see the entire function at once, optimize it all, and then lower it into coroutine code. So that was really neat as well. Yeah, we've added const explorers. We have no excepts because again they do nothing. But that's the answers if you want to refer back to them later. So we put the writes to the variables in, and this is the compiler transformation, and this is for the coroutine we've just seen, which doesn't have any suspend points. So first of all, it finds the promise type by looking in coroutine, creates initial return promise type. It finds the promise type and constructs a promise type object. Then I think it actually does that on the heap if it needs to, with an allocation. Then you get the return object out of the promise type, and because we don't suspend, we return the return object all the way down here. Then we do the initial suspend, which we said we never suspend. Then the whole coroutine body is in this try catch. And so if an exception is thrown in the coroutine body, it gets past this unhandled exception. And obviously in our case, we didn't throw, so that never gets called. Yes?
Can you get access to the exception that was thrown?
Yes, you can use stood current exception, and that gets you the exception pointer, and then you can do what you like with it. Then you've got this return void call in here, so that's the coroutine, the co-return statement that gets transformed into promise return void. You've got the final suspend. I said before that suspending at the beginning and the end can be useful because it means that things stay alive, and it means that things don't start running until you're ready. Obviously, in this example, we didn't use that. So we wrote support for the simplest coroutine live in under 5 minutes, though I did know the answer. We introduced the promise type, which defines the coroutine behavior when constructing a return type, before executing the body, when co-return or co-yield is encountered, what to do with unhandled exceptions, and after executing the body. And this is the coroutine's behavior. And so you can imagine the behavior for generator would be different because these functions are implemented differently. The behavior for task is different because these functions are implemented differently. And we looked at the compiler transform briefly to get an idea for what the compiler is actually doing under the hood. Obviously, there's more to it than what I just showed you, but that's a good summary to be thinking about. Let's now move on to writing the simplest gRPC coroutine. So just as before, the simplest coroutine was just co-return. This one is also just co-return. Only this time, we're co-returning a gRPC status, and then the gRPC runtime will return that status from the server to the client. We're going to call this the everything's okay service, because all it does is return okay. I think everyone's quite happy when everything's okay. It's useless, but it does allow us to focus on the support code because there's nothing else going on in here. We're writing a unary because there's one unary call because there's one request and there's one response, and that's so we've got this unary reactor here, and we've got the request and response in the body already. So why do we want to use coroutines for a unary RPC? Well, like I said before, if you use the synchronous one, that's a thread per simultaneous RPC, whereas this one is multiplexed onto a thread pool. And you can also use other async coroutine code in the implementation. So if you wanted to wait for 5 seconds before telling people everything is okay, maybe you like to suspense, then you can use your co-await in that from your async timer library. So where can we put the promise type? Previously, we put the promise type directly inside initial return, but this time the gRPC runtime says what the return type must be. So we can't modify that type, so instead we're going to specialize to coroutine traits, and that's really quite straightforward. So we've got our coroutine traits here, we've got our return type, we've got our argument types, and we say to the compiler, when you encounter a coroutine with this signature, the promise type you should use is server unary reactor promise type. And that's something we're going to have to write. So that's just hooking things up. And obviously, you've got the return type as the first parameter, you've got your function parameter types as the subsequent parameters. That's the promise type. And you can, if you wanted to make it generic for no matter what the arguments were, if you just wanted to depend on the return type, obviously you can use a variadic template. So this is what the promise type looks like. And it's been split into two halves here. On the right-hand side, you've got the coroutine machinery that we saw before, these 5 functions. So when we get the return object, we make a new unary reactor and return the reactor. And that's very similar to the code we saw for the reactor before. Initial suspend, we suspend never. And that's because we're kind of already on an executor. And also the gRPC library doesn't know about coroutines like this, so it wouldn't know to resume us. So we need to get going immediately. But it's okay because we're already on the executor. When we hit co-return status, this return value that takes an argument of status is called, and we just finish with the status. If there's an unhandled exception, we're going to finish with a status saying there's been a problem. And when we reach the final suspend point, we're not going to suspend either. We're just going to keep running off the end. This finish function here just calls the finish function on the reactor and then clears the reactor, so you can call finish multiple times. And because of the design of coroutines, actually there's no worries about reentrancy. I can go into that later if anyone wants to talk about that. Finally, if the reactor promise gets destroyed without having been finished, we finish. Yes, this is our reactor now, and all we have to do is, when finish is called and then the onDone callback is called, we delete this, which looks really weird. It's just a standard gRPC idiom. It's actually perfectly legal to do this. Obviously, it's legal to do this, but it does look weird. So this, as I said, this outline on the right-hand side is very similar to what we saw in the promise type before. We're using suspend never, like I said. We always need to call finish, otherwise we're going to leak this unary reactor. So all of the paths out of the coroutine, finish gets called. The reactor code is very simple. So we've added coroutine support to unary RPCs in a page's worth of code, 2 pages worth of code.
Where are you releasing the reactor? Where are you releasing the reactor memory?
It's the delete this here. So you call finish, and then the gRPC runtime calls on done and says, I'm done, I don't need this reactor anymore, at which point we can clean ourselves up. We implemented a basic gRPC promise type, and that was really straightforward. We just return the reactor and get return object, and then everything else we don't really do that much, we call finish. We saw that the reactor side of the code is really simple. Any questions about that basic case? Yep.
Same. Could you just go to the previous example?
You want the code or this?
Yeah, the one with the delete this.
Yeah.
If I decide to use a smart pointer and the end reactor is a unit pointer, for example, do I get to write this unary reactor?
So you would need to pass the smart pointer into the unary reactor because the unary reactor needs to manage its own lifetime. So I've just taken the easy way.
So as opposed to returning if I call it .get on the
If you call .get, then if you created a new smart pointer here. So again, one thing is when finish is called, this reactor needs to live until on done is called, so the reactor might outlive the coroutine. And so if you created the unique pointer here, then it would get cleaned up here. If you made it a member variable, it would get cleaned up when the coroutine was cleaned up. So we need to manage the lifetime inside the reactor ourselves. So yes, you're right, you could pass a unique pointer into the reactor and .get here and call reset here, but it amounts to the same thing. You've got an object managing its own lifetime and cleaning itself up. And that's fundamentally something a bit weird. Right. So we saw not sending any responses. Let's now send one response. And this generalizes to sending many responses. So this is now a server streaming call. So we've got a server write reactor we need to return. So our plan, like we said before, for this co-await send response is to suspend the coroutine. And only once the coroutine has been suspended, we call reactor start write. And then we're going to resume the coroutine in on write done. Yep. There's a problem here in that we need to be able to access the reactor to call start write. But the reactor lives in the promise type. That's where we stored the pointer to the reactor we used to call finish, and we need to use that same pointer to call send. So how do we get access to the reactor? I'm going to leave that with you for a second. I'm going to talk about awaiters and awaitables. So in order for co-await send to work, the result of this call needs to be an awaitable. I'm not going to go into the jargon too much. An awaitable is something that is or that can be transformed into an awaiter. It's complicated. I'm going to ignore that and make send return an awaiter directly. And an awaiter just has to implement 3 member functions. Obtaining the awaitable and the awaiter can be complicated. Like I said, I'm not going to go into it, but there's operator co-await, and that's kind of like yeah, it's kind of like an implicit conversion. You can think of it that way. And there's also this promise type await transform. And because it's in the promise type, that's defining the behavior of the coroutine as a whole. So again, we're not going to go into that. Just they exist. You can read up on them if you like. They're not useful for what we're doing today. I'm already quite late into the talk. So the compiler transformation, when you actually call co-await with an awaiter, the compiler converts into this. So await ready is an optimization opportunity. So you only suspend if you need to suspend. So if you're waiting on a timer, but the timer has already expired, then you don't need to wait, and you can avoid all of this compiler magic and calling await suspend and all this kind of stuff. It's an optimization opportunity. Await suspend returns a value or returns void, and that's really quite complicated. But basically, you can either return to the caller, which is what we saw coroutines doing before. You can resume this coroutine. So if you realize in await suspend that actually your timer has already expired, you can just keep on going with your coroutine. Or you can resume another coroutine. And that last one is really important for nesting coroutines, something called symmetric transfer. Again, I'm not going to go into it. The coroutine handle can be used to resume the coroutine or destroy the coroutine or access a promise type. So the compiler supplies the coroutine handle to awaiter.await suspend. And a neat thing to notice is that the coroutine is suspended at this point. And so it would be safe for the resumer to resume the coroutine immediately it gets the handle. And this addresses your question earlier. And finally, await resume provides the result of awaiting. It's always called. You can do some tidying up if you need to. And it kind of makes sense that it's always called because that's how you get the result. If you didn't call it, how could you get the result? So this is what we need to change, what we need to write. So in our await suspend member of our awaiter, what we do is we grab the promise from using the coroutine handle. We then reach inside the promise and get the reactor and stash our coroutine handle, or a copy, inside the reactor. And that's so the reactor knows which coroutine to resume when onWrite done is called. And then finally, we start our write. And if the write returned immediately, then it would still be fine. And then in our onWrite done callback in our reactor, we just resume the coroutine handle that we stashed earlier. Does that make sense? We've arranged for the coroutine to be resumed, and then in the callback, we're actually resuming it. So that just does what I just said. One thing to notice is that we're storing a reference here and passing a pointer here. Looks weird, you might think there might be lifetime problems, but actually remember that the response is a variable or a temporary variable inside the coroutine body, and we said the value, the variable is kept alive across the suspend point. So we're fine with our reference and our pointer here. And that makes it much easier to write than the reactor code you saw earlier where we had to make it a member of the class. So this is the full awaiter code. We've got await ready, and we return false because we always need to wait. We've got await suspend that you've already seen, and in await resume, we're returning void. We don't need to do anything. We've got the reference to the response so that we know which response to send when we call start write. And then this send function, all it does is returns an awaiter with a reference to the response we want to send inside it. Yep. Similarly, in the reactor, it's straightforward. In the onWrite done callback, if it's okay, we resume the coroutine handle. If it's not okay, we destroy the coroutine handle, and we don't do anything else. And remember, when we destroy the coroutine handle, the promise type is destroyed, the destructor's called, we call finish, and we finish with a response with a status of cancelled. Does that make sense? The rest of the promise type is exactly the same as in the unary case. And that makes sense because the overall coroutine behavior is the same. It's the same general idea, just with a bit extra in the middle. So this is what we saw before. I'm not going to go through it again, but this is to remind you. We call start write, and then on write done, we resume the coroutine. You've seen this before. So summary, we introduced awaiters and awaitables. We wrote an awaiter that suspends the coroutine, starts writing response, and then schedules the coroutine to be resumed when the write completes, when it's awaited. And we saw that the reactor side of the code is quite simple. We just had to add one function to handle the onWrite done callback. And we saw that the promise type side of the code didn't change because the behavior remains the same. Right, I have just over 5 minutes left. This is the finishing up section. This is what you can do after this talk. So we integrated coroutines and gRPC. We wrote some pretty straightforward support code. It's a few pages of code. It's mostly self-explanatory if you know how the coroutine bits fit together, and that's always a difficult bit. It can be understood and built on, and you can support most of gRPC in a few hundred lines of code. We've had an example of adding coroutine support to callback style async code, and we saw that how you add coroutine support is you stash a coroutine handle somewhere when you start the call, and then in the callback, you resume the handle. Yeah? Hopefully, you'll feel empowered to take the techniques I've just shown you and apply them to your own callback style API. And then you can integrate your callback style API with other coroutine code. And on the next slide, oh no, it's not. Where could we go from here? There's lots of options. build, highlight, inspire. So we could add support for the rest of the server operations. So we added support for returning status and writing. We could add support for reading. So if the client's sending more than one request to you, you can wait for requests to come in. But they all follow the same pattern. You've got a start operation call that you need to call, and then when the asynchronous operation completes, on operation done is called. We could add support for client operations. A little tiny wrinkle with client operations, but it's very similar, and it's not difficult to add support for them. And then finally, gRPC has timers built in. They're called alarms, and they can be used for doing async sleeps. Like that's what I said about waiting for 10 seconds, then sending your response. We could make the reactor more flexible. I'm going to rush through this a little bit because I want to get on to the rest of it. I've not got much time left. So what I mean by coroutine aware functions is that they kick off the operation, they return an awaitable, and then you can co-await the awaitable. And that's an eager coroutine aware function. And I think this is kind of how coroutine aware code is expected to work. You have an option of an eager or a lazy one. And actually, there's a nice thing you can do with the eager one. You can split it. So you can start your write in one place, the write's going on in the background, and at some point later, you wait until the write has finished. And that allows you to do other stuff while the write is going on. So in this one, we start our write, we start and wait for a read, we prepare our next response, and only then do we check that the write we kicked off initially is finished. So you've got a write and a read in flight at once. And then once that write has finished, we can start writing the next response. And so you can overlap things. Obviously, though, you can get this wrong, whereas with the simpler code we saw before, you couldn't. So Larry Wall says, make easy things easy, make hard things possible. So the default way of using it is co-await send, and it just does it when it's suspended. But if you really need to, you can overlap things using this. There's cancellation. I haven't talked about cancellation, but obviously if you've got an asynchronous call happening and the client cancels, you want to stop what you're doing as soon as possible so you can free up resources for another call to be handled. gRPC has a cancellation callback. It's called onCancelled. You can use this to cancel non-gRPC operations. So if you were waiting on a timer and the onCancelled callback is called, you cancel the timer wait or just destroy the coroutine. You can use cancellation tokens. Let's close most codes. Right. Penultimate slide. C++23 has the generator. The support for it's not very good yet. That's the only library support we have for actually using coroutines in user code. There's BoostAsio, which I've mentioned a couple of times. It's got support for C++20 coroutines. It's quite nice to use. You can do async reads, async writes. You can do timers, all that kind of stuff. But it's a walled garden. You have to use BoostAsio all the way. You can't take your own coroutine code and await it in a BoostAsio coroutine. There's Asio gRPC, which we're looking into, which integrates gRPC with BoostAsio. We make quite a lot of use of BoostAsio at our company. And we think it might be a nice way to go. There's Boost Cobalt. I've not used it. It's quite opinionated. It's quite open, where BoostAsio is closed. The cppCoro, which is like the grandfather of coroutine support libraries. There's a maintained fork. It was originally written by Lewis Baker, and it's now maintained by Andreas Burr. It's quite low level. It's lots of vocabulary types. It's worth a look if you want to understand what you can do with coroutines. And find there's libunifx, which is, as I say, experimental. There's some coroutine bits in there. There's these websites I found very useful. So Lewis Baker wrote a series of blog posts that have a really in-depth dive into how coroutines work, why they're the way they are, why you need to write all of these functions. Raymond Chen has a coroutine series, which is shorter articles, and he builds up things over a number of articles. It's really quite useful. It's based on like WinRT, but it's applicable to general coroutines. Find the CPP reference, but that's obviously more of a reference than a learning tool. But obviously I use it a lot preparing this talk. That's it. Thank you. I've got 1 minute for questions.